let's look a little more carefully at the definition of convergence, and also we'll look at a definition of divergence. So the context is that we have a sequence, and I'm going to use the full notation an n equals 1 to infinity, and a series, which is the sum of all those values from the sequence, and then the partial sum, which is sk, the kth partial sum, is the sum of the first k of those terms. So that's what we need for this definition. And so it goes something like this. If the limit as k goes to infinity of sk is equal to s, a real number. Then the series from n equals 1 to infinity of an is convergent or converges is another way to say it. There's the adjective. A convergent series, and equals s. It equals that limit value of the partial sums. S for sum, sk for partial sum, but this is equal to that number if the limit exists and is a real number. If the limit as k goes to infinity of sk, the limit of the partial sums, equals plus or minus infinity, or doesn't exist, then the series is divergent. So if the limit of partial sums is a number, the series is convergent. That's what it's equal to. If the limit of the partial sums is not a number, positive, negative, infinity are not numbers, or if the limit doesn't exist, also not a number, then the series is divergent. The series that we looked at was a convergent series. The terms of the sequence were 1/2 to the n, so we were looking at the sum of 1/2 to the n. We found a formula for the partial sums, and then we took the partial sums. Then we took the limit using that formula to find that the limit was 1, and that was a convergent series. The issue of the sequence itself being convergent is different. We'll have to look at some examples later to decide what the relationship is between the convergence of the sequence and the convergence of the series. And we're really just interested in the convergence of the series. I've got some examples that are from the text, page 452. There's an A and a B, so we'll look at those next. So from page 452, this is part A, and we're going to look at the series, the sum from n equals 1 to infinity of n over n plus 1. Did not leave myself room there, so I'm just going to continue. That's equal to, and I'm just kind of supposing that it's a real number. If not, we'll see, but let's list out some terms. So for n equals 1, I've got 1 over 1 plus 1. And in fact, let's write it like that. 1 over 1 plus 1 for the first term. And then when n equals 2, that's 2 over 2 plus 1. 2 over 2 plus 1. Plus 3 over 3 plus 1. Plus 4 over 4 plus 1. That's really just the pattern that's given to us in terms of the sequence. But let's also look at these as simplified fractions. 1/2 plus 2/3 plus 3/4 plus 4/5 plus 5/6 would be the next one. See, the numerators are incrementing, and the denominators are also incrementing. They're just one greater than the numerator. Another way to say this is that the terms of the series are n over n plus 1. That's my an. But what I'm more interested in are the partial sums. So I'm going to start looking at them in order. S1. The first partial sum is just the first term, 1/2. The second term, the second partial sum rather, the sum of the first two terms, 1/2 plus 2/3. And we could combine those fractions, but I'm not going to do that. I'm going to come back to this in a moment. Let's just list out a couple more. The third partial sum, 1/2 plus 2/3 plus 3/4. And the fourth partial sum, S4, is 1/2 plus 2/3 plus 3/4 plus 4/5. And like I said, you could combine these into a single fraction. Let's just look for the pattern here, and we'll use what we've got here. In general, though, we can go to the general term or the kth partial sum, an arbitrary partial sum, 1/2 plus 2/3, all the way up to well, what's the last one? Look here, the S2 has 2/3 for its last one. S3 has 3/4. S4 has 4/5. It's the index, the k value, matches the numerator of the last term, and then the denominator is one greater than that. As are all these terms. It's the number and then one number larger. Number and one number larger. But the last one is k over k plus 1. K over k. K over k plus 1. And now we're going to do something clever to see why, well, we'll see what. First of all, this one is greater than 1/2 plus 1/2. Is that true? Yeah, that's 1/2 is smaller than 2/3. So 2/3 is greater than 1/2. And this one I'm leaving the same. I'm just saying that if I replace this one with 1/2, that's going to be smaller. Here, this is greater than 1/2 plus 1/2 plus 1/2, because both of these are greater than 1/2. This one is greater than 1/2 plus 1/2 plus 1/2 plus 1/2. That's 3 times 1/2. I'm a little bit low on space, but you can see that these partial sums are each greater than, well, that's 2 times 1/2, and that's 3 times 1/2, and that's 4 times 1/2. This one's going to be greater than k times 1/2. And that's not a formula for my partial sum. What I'm saying is that my partial sum is greater than that. it's even bigger. But we're going to see in a moment that this goes to infinity, so something that's larger than it has to also go to infinity. And what I'm saying there is that the kth partial sum is greater than k times a half. So I don't want to say that the limit is greater than the limit, because that's not actually true. They're both infinity. What I'm going to do is show you that this is infinite, and since each of these is greater, this isn't, the limit of this is infinite. So since each of these are greater than each of these, the limit of these also has to be infinite. What I'm saying is the limit as k goes to infinity of k times 1/2 is infinity. Look, it doesn't really matter multiplying it by a half. It's smaller, but as k goes to infinity, this expression goes to infinity. So the limit as k goes to infinity of sk equals infinity also. Because I have a smaller, we looked at the squeeze theorem. This is kind of like that, except that it's squeezing up. Instead of squeezing between two sequences, we're squeezing it up toward infinity, or infinity is not a good sequence, but between infinity and anything else, the limit's going to be infinity. So, since the sequence of partial sums is not a convergent sequence, remember, if it's plus or minus infinity or doesn't exist, well, this one exists, but it's not a real number. It's positive infinity. The series, the original series we were looking at here was from n equals 1 to infinity of n over n plus 1 is divergent. And that's really the answer there, divergent. Usually the interesting thing about a series is it convergent or divergent? If it is convergent, what's its value? What does it converge to? That's a different question. For most of these, at first, we're going to be looking at convergent or divergent. There are some exceptions, but not yet. I want to look at part B of this example. Which is the sum from n equals 1 to infinity of -1 to the n. And we can look at this as a sequence. -1 to the first is -1. -1 squared is 1. -1 cubed is -1, -1 to the fourth is 1. And it really just goes on and on like that. I'm summing -1 and 1, and -1 and 1, -1 and 1, just because of whether n is even or odd. I get -1 for n odd, 1 for n even. I can look at the partial sums. The first partial sum is -1. Just the first term. The second partial sum is -1 plus 1, just the first two terms, which is 0. The third partial sum is -1 plus 1 plus another -1, And that comes out to one of these cancels with that, and I get negative 1. S4, negative 1 plus 1 plus negative 1 plus 1 brings me back to 0. So as I look at these terms, I'm really not going to find a formula for the kth partial sum. It just has to do with whether or not k is even or odd. Negative 1 if it's odd, 0 if it's even. There are ways to write that as a formula, but it's more useful just to look at it as the sequence of partial sums, and we'll be able to see just with those numbers. So this isn't negative 1 to the n. These numbers are negative 1, 0, negative 1, 0, negative 1, 0, etc. They keep going back and forth, not between negative 1 and 1, like the original series terms, but the partial sums go back and forth between negative 1 and 0. And you can see from that the limit as k goes to infinity of sk, is it approaching a number? No, it's kind of approaching two numbers, but it's always going to the other one, so it does not exist. It's one of those limits that alternates back and forth between two values. So this sequence doesn't have a limit. The limit of the partial sums doesn't exist. So the sum from n equals 1 to infinity of negative 1 to the n, the original series up here, is divergent. We found another divergent series. Part C of this problem, well, we'll see. With part C, we'll look at another infinite series which has terms 1 over n times n plus 1. This is part C. And we're going to use some old tools from maybe even Calc 1, but definitely some older ones from Calc 2 to work on this. Let's write it out as, what do its terms look like? Well, for the n equals 1, for the first term, that's 1 over 1 times 2. N is 1, so n plus 1 is 2. 1 times 2, 1 times 2. And I'm going to write it like that at first. And the second term, 1 over. N is 2 for the second term. 2 times, plus 1 is 3, 2 times 3. The next term, n is 3, so 3 times 3 plus 1 is 4, plus 1 over 4 times 5, and so on. Let's look at it a little bit cleaner. 1/2 plus 1/6 plus 1/12 plus 1/20. The next one would be 1 over 5 times 6, which would be 1/30, and so on. We'll be able to see the pattern in a different way, but if you need to list out more numbers to see the pattern, sometimes you can. I don't see anything really going on here. What I'm going to do next, the AN, by the way. The underlying sequence is this 1 over n times n plus 1. We're going to look at the partial sums. which are just what we get from adding together. Well, for the first one, it's just the first term. For the second one, it's 1/2 plus 1/6. And that is, this is 3/6 and 1/6, that's 4/6. The 4/6 reduces to 2/3. And this is the pattern that we're really going to see something useful in. The third partial sum, 1/2 plus 1/6 plus 1/12, and you could just add this 1/12 to the previous partial sum, because right there, that's S2. You can just add on the next one to get the, I'm going to look at these as all as twelfths. This is 6/12 and 2/12. 6 and 2 is 8. And 1/12. 9/12. 9/12 reduces to 3/4. Take your time if you want to pause and work this one out. 1/2 plus 1/6 plus 1/12 plus 1/20 is, that's the first 4 terms of the sequence. 4/5. And with that, you might be able to spot the pattern. What's going on with these is when I add those fractions and simplify, I get, for the kth partial sum, notice where these k values match, or where the index values match. The numerators are the same as the index, and the denominators are 1 greater. It's k, that's the numerator, k equals 4, equals 4, and then over k plus 1. The denominator is 1 greater than the numerator in all of these. That's the pattern that we're going to take advantage of. Next, let me keep that on there. And just look at the limit as k goes to infinity of sk. That's the limit as k goes to infinity of k over k plus 1. So I found a formula for the kth partial sum, sk. Now I'm going to look at the limit of that formula, larger and larger partial sums. The limit of that is, we use the fractions to find our pattern, but we're using the limit to find our value. Well, that's no good. If I look at the limit of this, as k goes to infinity, k goes to infinity. But also k plus 1 goes to infinity. That's infinity over infinity. That's no problem. That's what we call infinity over infinity indeterminate form. I put it in quotes because it's not really a good mathematical expression other than it's kind of what's happening. But I can use L'Hopital's rule. Since the limit as k goes to infinity of this is this indeterminate form, I can take the limit of the ratio of the derivatives. Now the derivative of k is 1. The derivative of k plus 1 is also 1. And that I can evaluate. The limit as k goes to infinity of 1 over 1 is 1 over 1, or it's just 1. So, the series is convergent. And I'm going to write it down here. N equals 1 to infinity of 1 over n times n plus 1 is equal to that limit of the partial sums.